This is question number 19 from the mid-semester. So we're trying to find a confidence interval. It's our first of the confidence interval / hypothesis test questions. We're given that diameters of a particular type of bolt are normally distributed with a variance, a population variance of 0.03 millimeters squared. That's going to be important. A simple random sample of 20 bolts is selected. The sample mean of the bolt diameter is x bar is 9.3 millimeters. Which of the following is a 95% two-sided confidence interval for the bolt? So the fact that we're told that the confidence that the sample size is 20 bolts might tempt you into thinking that we're going to use a t distribution here. But the fact that we're given that it's a normally distributed population and we're given the population variance means that we're actually going to be able to use a z statistic. If it's a normally distributed population but we don't know the variance, or we don't know the standard deviation of the population, we can still use a z statistic some of the time as long as the sample size is greater than 30. So that's the difference. If the sample size is greater than 30 and it's normally distributed, then no worries, we can use a z statistic all the time. If we don't know that value, then we would have to use a t statistic. In this case we do, so we're going to use the z. Let's go and have a look in the formula sheet for which formula we're going to use for our confidence interval. If you go to page 5 of the sheet that we're given for the exams and look at equation 60, if you look at the application, it's 100 1 minus alpha, so a 95% in this case confidence interval, so 5%, 0.05 alpha, two-sided confidence interval for the mean of normal distribution. And if you look at the cell next to that, just to the left, that sigma can be replaced by sample standard deviation when the sample size is greater than 30. So exactly what I was saying a moment ago. So if the sample size is less than 30 and you don't know the population standard deviation, then you can't use this formula. But if you do, then you can. So let's just write out what this formula says in case you're not looking at it or you're too lazy to get it. It says that, well, it's looking a bit ugly. It says that on the right hand side of that equation it's got 1 minus alpha, so it's a 0.95%, and on the left hand side it's sort of a probability. I'm just going to write out the confidence interval that we're looking for. It says that our confidence interval of the mean, so our, if I get notations wrong, I apologize, I'm bad at them. The population mean is given by our sample mean plus or minus this error factor, which is in this case is z of sigma over root n, and that's it. So we're given that x bar is 9.3 plus or minus this thing. What's that? First we need the z value, so we're going to go over to our tables. This is probably the third or fourth last page from the end. Basically at the start of the t tables it gives you some useful values for alpha and the z-score at the top in those little bars. It's got alpha as 0.1, 0.05 and 0.01, and then it's got the z-score corresponding to a two-sided interval using that alpha. So in this case we're looking for 0.05, so our z of 0.05 divided by 2 there, the second row is 1.96. That is our two-sided interval. So remember those three things are a two-sided alpha z-score for a particular alpha. Hope that made sense. 1.96 multiplied by our variance, which in this case, don't be tricked, is the square root of 0.03. Don't be tricked into forgetting the square root. And root n, which is root 20. If we type all that in, we're going to get 9.3, well, let's calculate the other bit first. 1.96 times square root of 0.03 divided by square root 20 is 0.076, 9.3 plus or minus 0.076, and I can already see straight away from that that's that the upper limit's going to be 9.376, so we don't really have to go any further because that's told us that the A is correct. So that's it for that one. Hope it made sense.